You're listening to the FQxI podcast. Today,
clearly our brains aren't sort of built to visualize that. We're just scratching the surface here. So I could absolutely see this opening some doors for new areas of research.
we continue our review of the year's biggest physics advances.
He's right. He's absolutely right. He is absolutely 100% right. Which is really pretty amazing when you think about it, because neutrinos are so difficult to detect.
With quantum physicist Ian Durham.
Basically, they swelled up larger than we expected them to before they burst. And the answer is there's nothing wrong with the data from the 70s and the 80s. There's something wrong with the theory, but we don't know. None of the theories so far match the data.
I'm Zia Morali. Welcome to the podcast from the Foundational Questions Institute. This is part 2 of our pick of the physics highlights of 2023. If you missed part 1, you can find it on the podcast page, qspace.fqxi.org/podcasts, where we discussed a handful of talking points that didn't make our top 5. Back with me again in this episode is Ian Durham, a quantum physicist at St Anselm College in New Hampshire, who spends each year noting down the biggest stories as they happen for this very podcast. Hello again, Ian. I think we still have a few more runners-up that haven't made your top 5. So, what's next?
Okay, so the very nearly got into the top 5. The first is this really interesting result. One of the headlines referred to it as Mathematicians' Complete Quest to Build Spherical Cubes, which, of course, what does that even mean, right? Anyway, back in the 4th century, there was this Greek mathematician named Pappus of Alexandria. He praised bees for their, quote, geometrical forethought, because it seemed to him that the hexagonal structure of the way they make their honeycombs is like the optimal way to partition two-dimensional space into cells of equal area and a minimal perimeter. And so this is an old problem. Nobody could prove that hexagons were optimal for literally millennia until 1999, when a guy named Thomas Hales, or Hales, I'm not sure how to pronounce his name, showed that no other shape could do better than a hexagon. This is actually a problem of tiling, which is something that we will discuss later on in our...
Spoilers!
Spoiler alert, yes. The idea of the two-dimensional case is, what shape can you cover a surface with that maximizes the area but minimizes the perimeter? We know that it's the hexagon, but we don't know what it is for three-dimensional cubes. And this is actually called the cubical foam problem.
And there are practical reasons for thinking about this too?
In fact, it even has a wide range of applications, including studying soap bubbles, analyzing the structures of crystals, understanding sphere packing arrangements. There's a famous problem that I think may have been mentioned on this podcast once in the last decade or something, the Keplers sphere packing problem. And there's some back and forth and back and forth and back and forth. But mathematicians have finally found that the optimal way for doing this in 3 dimensions is not the 3-dimensional equivalent of a hexagon, but rather a sphere. And it seems crazy, this idea of a spherical cube, that such a thing could even exist, but it does, at least in mathematics, because math is weird.
So is it, when we say a spherical cube, is that just a jokey name, or is it like a bubble that's been kind of squashed, so it's halfway between a sphere and a cube? Or what is it? What am I visualizing? Because I'm trying to imagine these things packed close together to tile a space.
So this is one of the problems with modern mathematics, is that it's so abstract, and it has moved to this level of abstraction where it's very difficult to say what it actually looks like. The math suggests that you're filling a 3-dimensional space with spheres, but clearly our brains aren't sort of built to visualize that, because even on the sites that covered this problem, what do? They show pictures of a bunch of spheres all packed together into, something that vaguely resembles a cube, but of course is just a bunch of spheres, balls that are sort of stacked. And of course, obviously, there's empty space in between those spheres. There was a visualization that was carried out by some mathematicians, well, researchers in Dublin, Trinity College in Dublin, that uses a shape called and I'm going to butcher the first name, Weir-Phelan structure, and it tiles a three-dimensional space with minimal surface area. It hasn't been proven to be the perfect tiling of three-dimensional space, but it's close. And essentially, if you look at them...
Okay, yes, I will put a link to those Weir-Phelan structures on the site. I'm looking at them now, and they sort of look spherical in the way that footballs, or soccer balls, as some people insist on calling them, look spherical, even though their surface is stitched together from pentagons.
Yeah, they kind of look like spheres. Maybe spherical-ish. In fact, the paper itself doesn't have a single picture in it at all. Like, it's just theorems and proofs and math. But where it matches up is the idea that there is a mathematical definition of a sphere. We know this. It's something that you learn in introductory calculus. Those ideas, only on a more advanced level, are what are used in the paper to show that, yes, the maximum way you can do this is through these spheres.
So well done to Asaf Naor at Princeton University and Oded Regev at NYU for that result. Nearly as good as the bees.
Nearly.
Right.
Are we up to the next one?
Yeah, we're up to the next runner-up.
Okay. Researchers recently found this sort of background hum to the universe caused by gravitational waves. The source is likely pairs of supermassive black holes that are spiraling towards one another, and they produce gravitational waves, which are ripples sort of in this fabric of the universe.
We've talked about gravitational waves before. So what is the relevance of this being a background hum as opposed to one of the other gravitational wave signals that, for instance, LIGO detected in the past?
So you can think about it this way. When the Big Bang happened, there's this leftover cosmic microwave background. There are these basically leftover photons from the Big Bang that were floating around out there that are like the background energy from the explosion of the Big Bang. Gravitational waves apparently have now been shown to produce something similar. The interesting thing is that they make a sound, I say sound with air quotes, because they leave a signature in the radio waves of these supermassive black holes or pulsars. And this result that was just published was actually based on 15 years of documenting the radio waves that come from these pulsars. The group that produced this, it's called NANOGrav. There's a slight caveat that a statistical measure of the possibility the results are due to random chance is a little bit higher than usual, but most people are pretty confident that these results will stand up and this won't need to be retracted. But there's this ever-present hum caused by the gravitational waves that leave their signature in the radio waves of these colliding supermassive black holes.
I thought you were going to say there's this ever-present worry that they might have to retract the paper, and that's just like, it's just going to run through the whole podcast now because of sort of the sad way in which we began. I have a quick question. When we talk about the cosmic microwave background radiation, so this is something that, you know, since its discovery, we've ended up with people whose entire careers are dedicated to measuring this more carefully and analysing it and studying it and finding all sorts of things about sort of the early universe and possibly, you know, thinking about its origins and thinking about all sorts of other things. Many FQxI members dedicate their lives to this. Is this similar in that sense? Could it have such a big sort of impact on science in general, on physics in general, on the careers of scientists? Or is it just, oh yeah, now we've detected this nice thing?
The mere discovery of gravitational waves opens up a whole new realm of astronomy and astrophysics based solely on gravitational waves. So, you know, up to now, all of astronomy, whether you are a visual astronomer, an X-ray astronomer, a gamma ray astronomer, a radio astronomer, whatever, you're working with electromagnetic radiation at some wavelength and frequency. But it's all electromagnetic. We now have gravitational waves, which have a range of wavelengths and frequencies. So this is like discovering a chunk of stuff out there that's at a particular wavelength and frequency. within the gravitational wave spectrum, and people have built careers on much less than that. We're in the infancy of studying gravitational waves. So we're just scratching the surface here. So I could absolutely see this opening some doors for new areas of research. And could someone build a career on this? Sure, why not? I don't know if it's quite the cosmic microwave background. Part of the reason that that is so important was its confirmation of the Big Bang model of a particular model of the universe and the universe's origin. I would say that these waves, they don't necessarily have a theoretical counterpart that they're like, whoa, this is smoking gun evidence for this particular theory, right? They're just predicted. But it doesn't mean that there's not really good science to be done here and that, there's a lot of discoveries to be made.
That's good. Another one to watch and to see how that pans out over the years. I think you have one more runner-up.
So this is an interesting discovery. So there are these things called phonons. And phonons they're a quasi-particle that are like, if you were going to quantize sound, right? What is sound? Sound is a vibration, pressure waves moving through material. So if you were going to quantize that, though, it's a wave, right? So if you're going to quantize it, you would get something called a phonon, which is basically a chunk of atoms that vibrates. And basically what this new research did is they were able to create a beam splitter for phonons. So what's a beam splitter? So in my lab with light, I have this little cube that has a mirror in the middle of it, and I shine a laser through it, and it splits the laser into two beams. And it does so in a particular way, in a quantum mechanical way that is random, in the sense that it takes photons that go in. The ones I have, 50% go one way and 50% go the other way, and you can't predict which photon will go which way. You just know that you get 50% in one direction and 50% in the other. And so this guy, Andrew Cleland, whom I actually happen to know, and his colleagues at the University of Chicago have basically created a phonon beam splitter.
So Andrew Cleland. I was going to just pick out a really nice quote he had, which is, a beam splitter is just a really bad mirror, which I liked.
He's right. He's absolutely right. He is absolutely 100% right. Andrew's a quantum guy, very involved in the development of quantum computers.
So is this a result that's useful for building quantum computers or something else?
This has some potential applicability in quantum computing. They actually have done a number of recent experiments that have demonstrated quantum effects with phonons. But this particular one is very interesting, that they have a beam splitter. And the assumption is that they could then create some kind of interferometer where you get maybe interference effects or something like that with the phonons.
So that brings us to the end of the runners-up, and we're about to go into the top 5. And I'm just thinking that, okay, so you left out the phonon beam splitter. And also, Andrew Cleland.
I know Andrew casually from APS March meetings, but yes.
Right. Well, the reason I'm bringing this up is that I'm thinking, well, let's say FQxI podcast countdown detractors might say, well, does it matter if you're a runner-up versus if you're in the top 5? Because, you're still kind of mentioned by FQxI, you're chosen by Ian Durham. Who cares if you're not really in the top 5? It's not like you get an actual prize, but we talk about this every year, right? We talk about whether we should give people badges. This year, following our rebrand and our redesign, we actually have FQxI merchandise. We actually could give out prizes to some of these people. And suddenly, the poor Phonon beam splitter team, they might be out of the running for an FQxI mug or tote bag or, even a t-shirt or a hoodie or a hat. We've, do you know what you've done here, Ian? I haven't mentioned this to you already because I didn't want to, bias you in any way, but we could think about actually giving prizes to the top 5.
I think that's a brilliant idea. I think it is an absolutely brilliant idea. They'll just get something in the mail and they'll be like, what is this?
I'm like, who cares? I won a Nobel Prize, but now I have an FQxI mug to go with it. That wasn't a spoiler, or maybe it was. Who knows? Maybe there is a Nobel laureate in our top 5. But yeah. So anyway, I will link to the QSpace site, qspace.fqxi.org, you can, click on shop and get your own FQxI merchandise. And if you wanted to, you could pretend that you were in the top 5 if you wanted to cheat.
Indeed.
But now the stakes have maybe been raised if we can be bothered to track these people down and give them some merchandise.
Indeed.
Who comes in at number 5?
All right, we have a sort of semi-tie at number 5. I say semi, I guess it is a tie. I did a little bit like the Nobel Committee sometimes does, is they'll wrap similar experiments together into sort of one big idea. The two things I'm looking at here for number 5 involve advances in nuclear physics that sort of shed new light on the nucleus and the proton. One is this: you can use neutrinos to probe the nature of protons, which is really pretty amazing when you think about it, because neutrinos are so difficult to detect. But you can use these neutrinos to actually measure the proton size quite accurately by scattering neutrinos off of the protons.
How do people usually image protons? Because we're sort of talking about imaging things using scattering and using neutrinos, and that's kind of weird because they're neutrinos. But what do people usually do?
Everything's a scattering experiment. So it's all about scattering. Everything's about scattering. So you can probe protons in lots of different ways. Every way boils down to you're throwing something at it and seeing how it scatters off it or passes through it. I mean, this is an age-old technique in particle physics going back to the early 20th century. You shoot something at it, whether it be light, it could be photons of various wavelengths, or it could be an actual particle, meaning a particle with mass. Either way, you're throwing something at it and then watching the pattern of how the stuff scatters, then using that data to infer the size and the structure of what you're looking at. The fact that it's a neutrino scattering is rather interesting. It's the Minerva experiment, which is a particle physics experiment at Fermilab outside of Chicago. What I heard was that there was a postdoc, Taejin Kai, who's the lead author on the paper, who was just in a meeting or something and said, hey, we could actually use neutrinos to do this. And someone else thought, all right, let's see if we can do it. Obviously, to do this, you got to have some very sensitive detectors, and you have to be able to, subtract out various background things. And they did it. They managed to do it. And so they were able to probe the size of the proton with neutrinos.
So I get why it's weird and interesting that they've used neutrinos, because neutrinos are tiny little things. They are very weakly interacting. They're supposed to be passing through humans and the Earth all the time, and they're really, really difficult to detect. But can you explain what's the advantage of using neutrinos in a scattering experiment? Because, they seem like a whole load of hard work. So what extra information can you get?
Well, so one of the advantages of using a neutrino is that they're electrically neutral. That they only interact in a very simple way. Let's say you were trying to probe the structure of a proton and you wanted to shoot electrons at it. Well, the problem is that electrons and protons have opposite charge, so they're going to be electrostatically attracted to one another, which is going to maybe throw off your results. It's kind of like trying to probe the size of a magnet by throwing iron filings at it. And the whole idea is you want some of the iron filings to fly by, but they're going to get sucked in, right? So you can't use electrons. You could, but it's not ideal. If you wanted to use another proton, well, then you have electrostatic repulsion. What they're trying to get at is the actual size of a proton. So you can't scatter something larger than a proton off of it. So the neutrino is sort of ideal in that, because the other thing is in the proton, you have the strong nuclear interaction going on. And so you don't want something that interacts strongly involved in that, because that could mess up what's going on. And so the neutrino is perfect. It really doesn't interact with much at all. Just enough that you can detect it, but not enough so that you don't have to worry about it screwing up your measurement. And it's tiny.
And did this neutrino scattering experiment reveal anything new about the size of the proton then, compared to previous attempts where they had probed the size of the proton by scattering with electrons?
Using the electrons, the physicists had incidentally been able to measure the proton's radius. They would list it officially as 0.877 femtometers. And if I recall, a femtometer is 10 to the minus 15. But the Minerva group had decided that it would be great to try neutrinos and or antineutrinos. Both neutrinos and antineutrinos are produced in different weak interactions, radioactive decays. It's specifically beta decay produces either a neutrino or an antineutrino. And these guys, so when they were using electrons, the 0.877 femtometers is inferred as the charge radius or the electromagnetic radius of the proton. The weak radius, as measured by the interaction with the antineutrinos, is 0.73 femtometers. So it's a little smaller.
So when you sent me your note about this, you'd written, nuclear physics simultaneously gets sharper and fuzzier. We've done the sharper part, so what about the fuzzier?
So the fuzzier, interestingly enough, there's still some curious questions about this. And I want to make it clear that unlike some of the other people we've talked about so far, the authors of this paper are very careful to hedge their claims and say that, we're fairly certain that this is true, but it's possible it's not. A theoretical physicist named Sonja Bakke at Johannes Gutenberg University of Mainz published a paper that suggests that there may be an issue with the typical theory of nuclear physics, and it has to do with this idea that one of the interesting things in nuclear physics is when we're talking about radiation, I mentioned beta radiation and that it produces neutrinos and antineutrinos. Alpha radiation is another form of radiation. What an alpha particle is literally a helium nucleus. It's 2 protons and 2 neutrons. It's a surprisingly strongly bound chunk of particles. And that's why when you have a very heavy nucleus, uranium or something like that, actually some of them are by a beta decay as well, but you have something very heavy, typically the nucleus itself, it can fracture and little chunks of it can come off. Well, it comes off in chunks that would be equivalent to a helium nucleus. It's 2 protons and 2 neutrons. Anyway, Sonja Bakke's work has suggested that the helium nucleus actually, when you excite them, they grow like a balloon until one of the protons pops off, or that's the theory. But then in a recent experiment, basically they swelled up larger than we expected them to before they burst. There's this measurement that describes the expansion. It's called a form factor. And she calculated that it's twice as large as theoretical predictions should be. And that kind of says there's something wrong in our understanding of how nuclear physics works.
And we don't know, we don't have any suggestions for why that might be happening.
Well, so no, actually, the answer is no. So Bakke, in 2013, she was actually able to use something called effective field theory, which is a way of approaching quantum field theory, to basically predict how much an excited helium nucleus would swell. She found, again, less swelling that had been measured, but there were these experimental error bars that were too big for her to be sure. But then what she did is she talked her colleagues into repeating these experiments, the original experiments from the 70s and 80s. And so they had new equipment. They wanted to do some updated experimental work and really try to see, really, was there a mismatch? So were these effective field theory calculations, which is the standard way of doing this, is there really something wrong with this calculation? Or was there something wrong with the data from the 70s and the 80s? And the answer is there's nothing wrong with the data from the 70s and the 80s. There's something wrong with the theory, but we don't know. None of the theories so far match the data. The calculation that came closest used a very oversimplified model of the nuclear force or nuclear interaction, which doesn't make any sense. But the thing is that even that one was still wrong. So the answer is we really don't know.
Intriguing.
One of the things about these top 5 is they should be things that really are foundational and deal with foundational issues, because we are the Foundational Questions Institute. So the phonon splitting and the cubical foam stuff and the
gravitational wave background hum
are all really interesting. Did they really cause us to change the way we think about physics? And there could be some debate about that. This result really does, because this result says there's something wrong. The other result with the neutrino scattering, that also does a little bit too, because, I mean, it doesn't necessarily suggest new physics per se, but it really does, it starts to shed a little bit more light on what's really going on deep down inside that nucleus, inside those protons and neutrons. And it maybe is a little bit surprising, just even in the fact that it could be done in that sense. But so I think these nuclear physics discoveries are sort of pushing the boundary here of saying they're addressing really deep foundational questions and maybe even raising new questions.
So that sort of gives you a hint of what the other four are going to be, at least in terms of their impact. But you will have to wait until the next episode to learn more about what they are. In the meantime, please head over to qspace.fqxi.org/podcasts for more information on the items mentioned thus far. And apologies, I have been sending you to the wrong link. It's podcasts plural, not podcast singular. So that's qspace.fqxi.org/podcasts. I'll put a link to our FQxI merchandise shop too, but it strikes me we've missed out on gift giving season. To the groups that have been mentioned in our top 5 so far, please do drop us an email on podcast@fqxi.org, or you can find us all over social media as either FQxI or FQxI Physics, and put in a request for your mug. You've earned it. For now, thank you to Ian Durham and to you for listening. I've been Zia Morali.